This briefing is a tactical deep dive into systematic restructuring required for hydrogen rich iron making. We are not just looking at the fuel swap, we are here to dissect how hydrogen physically and thermally alter the furnace from the tuya to top. So over next 15 minutes, we will analyze the kinetics of diffusion, the morphological shift from whisker to layers, and the specific thermal finds we pay for using a highly endothermic reducing agent. By the end, you will have the deliverables for a strategic roadmap, mastering raft compensation, re-engineering the center coke skeleton, and pinpointing the 10 to 15% gas injection sweet spot. So we have all heard the buzz about hydrogen, but well, is it just green? No, this is a fundamental shift in how the furnace actually breathes. Look at the blue arrow on the right. That's our hydrogen injection path. Notice how it cuts into a traditional burden layers, signaling systematic shift in thermodynamics and thermal profiles. We are moving beyond simple carbon reduction. We are entering a phase where the entire burden morphology is dictated by a lighter and faster gas. But before we talk about how we have to address the why, and it start with the massive carbon debt we are currently carrying. Iron making control the carbon consumption in a major way. Here the things about our energy bill that shows the blast furnace is primary consumer. That massive 67.94 of total steel making emission which shown in the slides comes straight from our floor. Sintering at 14% and coking at 7% are just fragments by comparison. Since the blast furnace dominates 4 to 7% of global emission, hydrogen injection is not just a nice to have, it is the highest leverage intervention we have in entire industry. Okay, so we need to inject hydrogen, but how do we get it in there without crashing the hearth? So you might think pure hydrogen is the only way, but we have option and each one has a catch. Look at this table. Natural gas has a high replacement ratio of 1.12 while heavy oil hits 1.2. Note the blue highlights. Every choice changes your calorific value and blast temperature requirements. Every gram of injection require a corresponding blast temperature increase. For natural gas, that's a 5 to 6 degree jump per gram. Geography and market price are now your primary constraint. Choosing the vector is a logistical game. The real challenge is the tug of war happening inside the chemistry of the furnace. The power versus the penalty hook. So, this is the core of the problem. Hydrogen has incredible power, but it comes with a massive thermal fine. Look at a chart A, the power, see that critical transition zone at 843 Kelvin. Now look at chart B, the penalty carbon monoxide reduction is exothermic, giving us heat, while hydrogen is endothermic, sucking it out. The thermodynamic impact says we are or finding are that we are looking at 23,834 kilojoule per kilomole for hydrogen reduction. It's an extraordinary reduction or reducing agent, but its severe endothermic nature breaks the traditional thermal equilibrium we have relied on for decades. So, if it's a stealing heat, why do we want it? Because of the sheer speed of those teeny molecules. So, coming to the overcoming diffusion resistance hook in the furnace, as we can see, we are looking at the cross section of an iron ore pellet. See those blue rays, those are hydrogen molecule effortlessly breaching the gas boundary layer and diffusing through the ephemeral and FeO layers. Because the hydrogen has a significantly lower density and 14 times higher reduction potential than carbon monoxide, the rate limiter shift. We move from chemical reaction control to diffusion control reduction. But speed is not the only win. Hydrogen actually changes the physical skin of the iron as it forms. Coming to the whisker versus layer. Why does the hydrogen get sticky and cause hanging? Coming to the question again, that why does the burden get sticky and cause hanging? It's usually because of these jagged whisker on the left. Look at the carbon monoxide mechanism. Bulky molecule disrupt the lattice, forcing iron to precipitate as tangled whisker. Now look at the hydrogen side. Clean diffusion, no mechanical displacement. And process reality is hydrogen generate a smooth, dense metallic shell. This drastically lowers the sticking index, which means fewer catastrophic agglomerations and a smoother moving burden. And if you think smooth iron is good, wait until you see what it does for our pellet. That is the not only pallet, it's pallet to the specific pallet expansion rates. So halting the halting the pallet expansion hook, if you see, permeability is on our lost in the pellets. But look at this difference. Under carbon monoxide, pellet expand by massive 2 to 4% at 900 degrees centigrade. Under hydrogen, that expansion rate drops to a mere 24%. Rapid transformation of Fe2O3 to FeO under hydrogen decreases internal gas pressure. The dense iron shell suppresses the whisker growth, preserving our structural integrity and permitting superior upward gas flow. It's all sounding great. Here is the trade-off. Start to hurt, starting with your sinter pulverization. Now coming to the trade-off. If pellet love hydrogen, sinter well. Sinter hates it. The five-step flow shows the catastrophic pulverization path. It starts with hydrogen penetrating surface crack and leads to an endothermic shock that induces severe internal stress. The water-gas reaction creates intense internal vapor pressure leading to a skeleton collapse. These degradation of upper shaft permeability demand a sticky high RDI resistance burden. Sinter is not the only thing under attack or structural skeleton. The coke is also in the crosshairs. So coke degradation, the water gas threat, is our topic of discussion in this slide. We usually worry about CO2 solution loss, but hydrogen brings a new villain, the water gas reaction. Look at the activation energy number. Conventional carbon dioxide reaction need 169 kilojoule per mole, but hydrogen rich pathway only 87. kilojoule per mole. So the structural consequence, uh, because the activation energy is roughly half, the coke structure is aggressively attacked much higher up in the furnace. So you must pivot to exceptionally high strength, low reactivity coke to survive this. With the burden and the coke changing, the entire temperature map of the furnace gets redrawn. So if you don't adjust your blasting, your furnace will catch a thermal cold. Compare the conventional blast furnace on the left with the high hydrogen blast furnace on the right. Notice how the 200 degrees centigrade to 600 degrees centigrade isotherm shift heavily downward, compressing the thermal reserve zone. Endothermic heat absorption uh, lowers the top gas temperature, triggering the RDI threat. Meanwhile, the raft drops significantly, necessitating oxygen-enriched blasting for heat compensation. A compressed thermal field means a compressed cohesive zone, and that changes the aerodynamics of the whole system. So here is the pressure paradox. You would think faster gas means higher pressure, right? Look at the droplet zone. In the middle of the cohesive zone diagram, it's compressing. But look at the blue arrow. The flow is actually easier. Despite higher actual gas velocity, the overall pressure differential drop. Why? Because the heavily reduced burden is so highly permeable that gas just zips through. So, how do we pull all these moving parts together into a winning strategy for the floor? So, the hydrogen rich blast furnace success is not a simple field swap, it's a total system reengineering. This blueprinted furnace summarizes our battlefront. Cool gas at the top, accelerated permeability in the shaft, and a raceway heat deficit at the bottom. The synthesized outcome are managed by these three things at once: the strict sinter quality, lower pellet swelling, and aggressive heat compensation via oxygen enrichment. We are not doing this in a vacuum. The global horizon is already shifting towards these systems. Coming to the global hydrogen iron making horizon, who else is playing this game? From hybrid in Sweden to course 50 in Japan and POSCO in South Korea, each project is tackling different gas ratios from 10% injection to complete BF bypass. We are moving towards near zero emission targets. Japan is already targeting 10% CO2 reduction through coke oven gas reforming. So, for our furnace, what is the day one roadmap for the operators? The strategic roadmap for the blast furnace operators is our next slide. So, this is your operational dashboard for the future. Three pillars: one, heat and draft management; two, burden and coke re-engineering; and third, limit optimization. So, what is the final directive? Hydrogen cannot fully replace coke, it is our structural skeleton. We must pinpoint the exact injection limit, usually a 10 to 15% gas ratio, before the thermal penalty collapses the process. So, which brings us our final takeaway. So, don't call it a fuel swap, it's a total reboot that Central red and blue circle represent the morphological restructuring of every single pellet and coconut in the furnace. Success belongs to the operators who manage the thermal and structural ripple effects, not just the chemical input.